Hello and welcome to Control System series. Today we are going to learn Lyapunov stability theorem. In this video, we will learn the Lyapunov stability theorem, which is used to determine the stability of an equilibrium point using an energy-like function known as Lyapunov function. Consider a nonlinear system in the form of x dot equals to the function f of x, where x is an n-dimensional real vector. We aim to prove using an energy-like function that a given equilibrium point is stable, asymptotically stable, or unstable without loss of generality, and for the simplicity of notation we assume the equilibrium is located at the origin. Alexander Lyapunov was a Russian mathematician who had an important contribution in control theory and in particular in the stability of motion. He proposed a method to determine the stability of an equilibrium point using a generalized energy function and without finding the trajectories of the system. Let's first see how the energy of a system can be used to examine the stability of an equilibrium point of a system. Let's take an example of a pendulum with these state equations. The potential energy of the system is mgl times 1 minus cosine of x1, and the kinetic energy is m times lx2 whole square. The total energy of the system, which is called V of x1 and x2, is a sum of the kinetic energy and the potential energy. A 3D plot of the energy of the pendulum is shown in figure 1 for different values of x1 and x2. The set of points which have the same energy are shown as black curves. They are called level curves or level surfaces, which are the set of all x1 and x2 such that V of x1, x2 equal to c for different values of c. The second figure shows the level curves of another angle. Consider the case where there is no friction in the system, that is k equals to 0. In this case, there is no dissipation of energy, which means V is constant. Therefore, the derivative of the V is also equal to 0. So if you start from an initial condition at which the energy is not 0, the ball will oscillate forever, and although the angle of the ball and the angular velocity remain constant, and therefore x1 and x2 remains on a level forever. We can then conclude that the origin is a stable equilibrium for this system. So, according to the stability definition, the origin is stable if for each positive epsilon there exists a positive delta, such that if the norm of x of 0 is less than the delta, then the norm of x of t is less than the epsilon for all the time. So, for any given epsilon, we first find the largest closed level curve inside the ball with the radius epsilon. For example, if you are given this epsilon, then we will choose this level curve, which is the largest closed level curve inside the purple ball with radius epsilon. We just saw that if a trajectory starts on a level curve, it will remain on the curve forever as there is no friction in the system. And if it starts inside the level curve, then it is impossible to leave the level curve as the energy doesn't increase. So, if we choose a ball with the radius delta such that it's fully inside the red level curve, then the trajectories of the systems always remain within the purple ball with radius epsilon. If, for example, we choose this green ball with the radius delta, the trajectories of the system starting within this ball remains for all the time within the purple ball with radius epsilon. In fact, the trajectory cannot even leave the white level curve as the green ball is fully within the level curve. This figure shows the largest epsilon we can choose initially if the initial condition is at point A, then x1 and x2 are always on the yellow level curve. But if the initial condition is at point B, then x1 and x2 are always on the red level curve, which is still within the purple bar with radius epsilon. So the origin is a stable equilibrium point. Okay, let's now consider the second case where the friction constant K is not 0. Due to the friction in the system, the energy decreases until it eventually reaches 0, which happens when x1 and x2 tend to 0 as time goes to infinity. So, if we have a system for which the energy decreases until it reaches 0, at an equilibrium, we can conclude the equilibrium is asymptotically stable. This is because equilibrium is attractive and is stable. Now, Lyapunov have showed that it's not necessary to use the energy function of a system in order to determine its stability. It's sufficient to use a generalized function or a Lyapunov function instant. Now we will have to explain what this function is. But before that, we need to make a few definitions. BR f of 0 is a set of all points which are strictly inside the ball of radius r around the origin. In the second space, BR of 0 is a circle with radius r centered at the origin, and in the third space, it's a sphere. A continuous function v is positive definite on BR of 0 if it satisfies two conditions. V of x is positive for all non-zero x in the ball and is 0 at 0. Similarly, it's negative definite on BR of 0 if V of x is negative for all non-zero x in the ball and is 0 at 0. Note that here V of x is basically a scalar function. A continuous function V is positive semi-definite on BR of 0 if V of x is non-negative for all x in the ball and is 0 at 0. The definition of the negative semi-definite function is similar, except that V of x is a non-positive for all x in the ball. Okay, now we will go through a few examples. In the first example, consider V of x is equal to x1 square plus x2 square. This function is 0 when x1 and x2 are 0, so it satisfies the first condition. It also positive for all non-zero x, so we conclude V of x is positive definite on any ball around the origin. In the second example, consider V of x equals to x1 square, where x is a 2D vector. V of x is always greater than or equal to 0 and 0 at 0. But there are points other than the origin at which V of x is 0. For example, if x1 is 0 and x2 is a non-zero constant number, then V of x is 0. So, V of x is a positive semi-definite on any ball around the origin. In the third example, V of x is equal to minus times x1 plus x2 whole square. V of x is always less than 1, then always less than or equal to 0 and is 0 at 0. But it's also 0 when x1 plus x2 is 0. So the function is negative semi-definite on any ball around the origin. Now we are ready for the Lyapunov stability theorem. The origin is a stable equilibrium of x dot equals to f of x if there exists a positive r and a positive definite function v of x on the BR of 0 with radius r, such that v dot is negative semi-definite on the ball, and if v dot is negative definite on the BR of 0, then the origin is asymptotically stable. So, if we could find the locally positive definite function v such that v is a locally negative semi-definite, then we can conclude that the origin is stable. And if we could find the locally positive definite function v such that v at the origin is asymptotically stable. A Lyapunov function is usually denoted by v or w and is a function from Rn to R. It should be noted that v dot can be calculated using the chain rule and is equal to the partial of v with respect to x times of f of x. If v dot is a negative definite function, then v decreases and goes to the next level curve as shown in these two figures until it reaches to 0. Since v is the only 0 at 0, x of t goes to the equilibrium point at the origin, which means that the origin is an asymptotically a stable equilibrium point. So that we can conclude, if we couldn't find a locally positive definite function v such that v dot is locally negative, some semi-definite or negative definite, can we conclude the origin is not a stable or not an asymptotically stable? The answer is no. Lyapunov stability theorem only provides sufficient conditions for stability. If we couldn't find a function that satisfied the condition of the theorem, we cannot draw any conclusion on whether the origin is stable or not. Okay, now let us consider a first order example for which the linearization method fails to work. The system model is x dot equal minus x cube. We first find the equilibrium point of the system. This system has only one equilibrium point at the origin. We choose a quadratic function in the form of v of x equals to x squared over to note that this function is 0 at 0 and is positive otherwise. So v is a positive definite function in R. We then calculate the time derivative of v using the chain rule. As we know that v dot equals to the partial of v with respect to x times x dot. The first term is x and the second term is obtained from the dynamic model of the system. So v dot equals to minus x4, which is 0 at 0 and is negative for all non-zero x. So it is a negative definite function in R. Using the Lyapunov stability theorem, we can conclude the origin is asymptotically stable. Second example, we study the stability of the pendulum system without friction. We choose v as the total energy of the system and choose the radius of the ball such that v is a positive definite on the ball. We can calculate v dot using the chain rule. Since x is a 2D vector, v dot equals the partial of v with respect to x1 times to x2 x1 times x1 dot plus partial of v with respect to x2 times x2 dot. We then obtain that v dot is 0 and therefore is a negative semi-definite as it also less than or equal to 0. So we conclude that the origin is a stable equilibrium point of the system. Okay, the summary of Lyapunov stability theorem. It is a very useful and powerful technique that not only determines the stability of an equilibrium but also provides information about the region of traction of an equilibrium. And the main drawback of this technique is finding a function v that satisfies the condition of the Lyapunov stability, which is not an easy way. Thank you very much.